Good morning, everyone. Thank you so much for joining us for this month's Seal Connect Classroom webinar. I'm Lori DeToro, and we have with us Chuck Tanner, who's going to be presenting on Mechanical Seals 101. Welcome, Chuck.
Thanks, Laurie. Thanks, everybody, for listening in today.
Absolutely, yes. Thank you for joining us. And before we get started, we're going to give time for everyone to log in. So, Chuck, I want to ask you a question that a lot of times I ask questions I think I know the answers to, but do you think people are intimidated by mechanical seals? And without giving too much of the presentation away, why do you think they are, if you think they're intimidated?
I think they are, Laurie. I think that's they look at these cartridge seal packages, and they don't understand the internal concepts on actually how they function. And it's it's a pretty intimidating piece of equipment if you really don't understand what the internal parts are. It's to some people it's almost like looking at a wristwatch and having to take a watch apart, and it's really pretty simple. And we're going to go through some things today to simplify and take the mystery out of these items for people, and so they can kind of understand what all the parts do and what all the components are internally.
And that it's actually pretty simple.
Pretty simple, no big deal.
All right, thanks so much. Let's get started. We are just going to go over a few housekeeping things, which we do at every webinar. This is Seal Connect Classroom. It is a non-branded educational webinar series that we host once a month. We use SEPCO experts, and we also have experts from outside the industry and outside of SEPCO and within the industry who come on and talk with us about different reliability topics, including leadership and equipment reliability and how to get started with reliability programs. So we're real excited about this classroom that we started this year, and we plan to continue it into 2022. Our next webinar for December will be on what data you need to collect when you're speccing equipment or getting ready or trying to do an ROI report to prove a case to your management. So that'll be our next webinar on December 21st, and we hope you join us. You can join the discussion on social media using hashtag SealConnect. Please ask questions on the sidebar on the right. There is a place for you to ask questions, and we will probably answer them all at the end of the webinar. But if something seems timely, I'll hop in and interrupt Chuck and ask the questions as they come in if we need to. But usually we try to answer all those at the end. On the right panel, there is a white paper that you can download on mechanical seals if you would like to. And we are recording the session, and you will get a copy of the slides with the recording sometime this week, probably tomorrow or Thursday. So take notes if you'd like to, but we'll also be sending you the recording and the slides for your use. I think that covers everything. So Chuck, I'm going to pass it over to you, and y'all get your questions in for us.
Thanks, Laurie. I'm Chuck Tanner. I'm the Director of Market Development here at SEPCO, and I've been in this business for many years. I've spent most of my time and most of my career in the pulp and paper industry, but I've been exposed to many industries during my career, and I hope during this discussion we can take some of this mystery out of mechanical seals. Mechanical seals have traditionally has kind of been this mysterious black magic that people don't really understand, and we're here to kind of make this a much more simpler concept for people to understand on how to spec them and how to review your recommendations. Some of the things we're going to talk about, we're going to talk about the reason to use mechanical seals. We're going to talk about exactly how they function. We're going to talk about single seals and the environmental controls to enhance their seal life, double seals and their environmental controls to enhance double seal life. We're going to discuss face combinations, going to talk a little bit about elastomers, rotary versus stationary designs. We're going to do some basic field pump identification. So when you go in the field and somebody shows you what a pump is, so you'll know exactly where the seal goes and what it does. We're going to talk about some of the fitting issues that you may encounter when you're in the field. And then we got one case study that kind of open up some subject matter that some of y'all may have never realized, but that's a basic agenda for today. Laurie, if you would take a minute and launch this poll, and let's kind of get a little feedback from people on how comfortable they are with mechanical seal technology, if you would.
I will. So the question is, are you intimidated by mechanical seals? Definitely want as many people as possible to answer this while we're here. We'll give everybody a few seconds to answer before we close it out and show the results. We're getting a little mixed bag coming in, which is nice. All right, I'm going to close the poll. And this is surprising to me, but we have 38% say they are intimidated, so less than I thought, and 63% say they are not intimidated. So there are answers.
Well, that's just proof that education makes life a whole lot simpler. Reasons to use mechanical seals. I mean, anytime you, in today's world, in today's maintenance budgets, anytime you make an improvement or make an investment in a piece of equipment to improve reliability or improve some kind of process situation, there has to be a reason to do it. And I came from a day when they just kind of bought seals to buy seals, but in today's economic environment, they don't do that anymore. It's more of some decisions go into buying seals and making this investment. Things that's considered is product loss. Does the product have a value, or does it is it a housekeeping issue? Does it result in a housekeeping issue? Does it result in that product loss result in deterioration of the bases, pump bases, equipment bases, and around the piece of equipment? Other things is product dilution. There's a lot of concern out there in some processes about adding water or any external source of fluids into that process. Mechanical seals, just by their nature and their smaller face contact footprint between the two faces, they use less energy. Packing has a much larger surface area that's contacted with your pump sleeves, and it requires more energy to move that. And of course, mechanical seals eliminate pump sleeve wear and some equipment corrosion issues that packing that's just inherent with the use of packing. And then some pieces of equipment you have to run seals in for safety reasons. You have processed fluids that are dangerous or carcinogenic or harmful to the environment. Those applications require mechanical seal. And then just general housekeeping. Some people run seals just to eliminate bothersome safety related housekeeping issues. Laurie? Oh, okay. The one thing you have to evaluate is a mechanical seal the most cost effective sealing solution. I mean, some of the things that you have to consider before you run a seal is are the plant personnel working with the seals trained to install and replace seals in the field. Some plants need additional training for their personnel to be up to speed to actually use seals. One of the issues with mechanical seals is a lot of the seal replacements, you have to pull equipment down and pull it offline and rebuild pumps and all that stuff that goes along with putting a seal in, that you have to experience quite a bit more downtime in a lot of cases than you do just packing replacement. And the other issue that you have to evaluate is the average seal life. Is it adequate to get a positive return on that investment? There's a reason to put a seal there. That reason is to make money on that seal. But you have to have, the seal has to run a certain length of time to have that positive return. We're going to talk in depth about this later on. Let's talk about things that affect seal life. Basically, what you're doing with a mechanical seal is you have a rotating face and a stationary face. All seals work this way. And what you're trying to do with those two faces, those two faces are lapped within 2 helium light bands. We actually read them with light bands here at the factory. And that is like 23 millionths of an inch in flatness. Well, so what you're doing, if you kind of picture this, is the fluid that you run across that face functions like a lubricating film. And it's the molecules are like little ball bearings that rub in between the two faces. And that's what keeps the faces lubricated. Anytime you deal with a seal and you're making a recommendation or you're choosing a seal face, always think about keeping that face lubricated. And if what you're pumping will lubricate the face, or if what you're running across the face is an external lubricant, will it lubricate that face? In the selection process of speccing seals, this is one of the most critical things that you have to decide when you are selecting faces, or how to handle and create a proper environment for that face to survive. As a user, that's one of the main things you've got to consider. Three factors that you need to look at when you are speccing a seal is the fluid temperature, the fluid pressure, and the fluid properties. Now, fluid temperature, some fluids have different characteristics at different temperatures. For instance, something as common as water. Now, understand something is you run that say just water across that seal face. That seal face, that water goes back to a vapor before it exits the seal. The seal actually leaks, but it leaks vapors. So that fluid temperature that you're running across there has to be cool enough to keep it cool. Now, water will keep it clean, but will it keep it cool? Now, just ambient water was not a problem. But when you take water that's 200 degrees, that is a problem, because you've got, at the faces, you have heat generated at the faces, and you're getting a pressure drop across that face. And as that water goes across that face, that water, due to the elevated temperatures as it crosses the face, goes back to steam at water at 200 degrees. So the water, when it goes back to steam, it expands like 600 times its original volume, and you end up with these little explosions in the face. So the fluid temperature of the lubricant that you're using, the product that you're running across the face, is critical, that you know what's going to happen to that product at elevated temperatures. Pressures, most everybody's off the shelf standard seal is balanced to run 150 psi to stuffing box pressure. Well, what I'm talking about when we talk about balance, they're balancing the closing and the opening pressures. So you only have like a 25-pound loading force even at 150 pounds. My advice is, if you have anything that has a stuffing box pressure over 100 pounds, I would consult with your mechanical seal supplier to make double sure that seal will handle those elevated pressures. And if there's something they can do to tweak the seal to get you a little bit better seal life. And then the fluid properties of what you're using to lubricate the face. You need to realize that some of these, that you got heat generated at the face, and some of these properties of fluid that you're running across a face may change when the temperature is elevated. For instance, like adhesives. Not that adhesives are good lubricants, or like latex. Those materials, as they go across a face, they dry out and they polymerize. In other words, they'll ball up. And when you take glue and rub it between your fingers, how it kind of balls up in between your fingers. It does the same thing in between those faces, just like latex. Latex will ball up, and it kind of dries as it goes across that face. So you got to realize the fluid properties of what you're trying to use as a lubricant. And you may not be able to use the process fluid as a lubricant. So let's go to the basics. Okay. In a single seal, you have a rotary face, which is represented by this red face in this illustration, and a stationary face. Okay. That's simply all you're doing. Is that all this other hardware you see around the seal is just a way for us to mount these two faces. All this other hardware you don't really need to be concerned about. Your goal is to lubricate these two faces and to get the optimum seal life out of these two parts that are running together. It's nothing more than a rotary union. And again, what's happening is the red face is rotating and the yellow face is stationary. All mechanical seals, single mechanical seals, work this way. This is the same mechanical seal that you've got in your washing machine at home, your dishwasher at the house, the water pump on your car, the seal that's on your pool pump. All of these seals function just like this, and that's all they are, is two precision lap faces. And what you're doing is trying to keep a cool, clean product running across that face to keep that face lubricated. Now, mounting them, this illustrates the use of a gland that holds the stationary piece. And that's what holds that piece and is bolted to the face of the stuffing box that retains that part to keep it from rotating. And we call that a seal gland. Back in the day, or you may run across applications where you have component seals. You'll have a separate gland and a separate rotary, but in most process industry today, everything is pretty much cartridge mounted. It eliminates all the installation irregularities, and it takes a lot of the human factor out of setting seal lengths and spring compressions and all of that stuff that goes on. That's the reason we cartridge mount everything today. And this gives you a basic illustration of a standard cartridge seal. You'll see the red rotary face and the yellow stationary face. All this other hardware you see is just mounting and engineering to make these parts adapt to the piece of equipment that you've installed in. All that stuff is done through engineering. Okay. Can you back up, Laurie? Laurie. Okay.
It should be
All
back
that.
to the original.
Okay. There we're back. All of these other components you see outside the seal face are engineered parts that's done by the seal company. The only other decision process you're going to have to make, there's two other things you've got to make, is how to set up the environmental controls and in selecting O-rings. That's the only two decisions you've got to make when you're mounting a seal. All of this other stuff is engineered and done by the seal manufacturers. When we talk about environmental controls, let me explain what we're talking about. We're talking about creating an environment in the stuffing box where the seal's mounted to maximize the seal life. And what we're doing with environmental controls is we're actually altering the fluid that's in that cavity around that seal to make that seal run cooler and make it run cleaner. That's all we're doing. And what we're doing is we're controlling the temperatures. We're going to show you some basic configurations on how to do this. We're controlling the pressures, and we're managing the properties of the fluid that's around the seal in single seal applications. One of the basic things that you see with single seals is an external flush. So if you've got a slurry, a product that's abrasive that that won't lubricate the seal face, you can use an external flush of something of a clean fluid. Most of the time it's water. Okay. And what you do is you inject the seals have a port in the gland that you run this water through, and it injects that fluid at the seal face, as you can see in this illustration, and it fills that stuffing box up with this fluid that creates a clean, cool environment for the seal to run. That's what you're trying to do. Uh, the only problem with this is that if you've got a process that you can't tolerate any dilution because you're not restricting this flow out the bottom of the stuffing box, you can't use this configuration in those cases. But here again, what we're trying to do is keep that area around the seal faces cool and clean. The other thing that you can do if you have a fairly clean fluid and you want to avoid the buildup of heat around the seal faces and in the stuffing box is you can run a discharge bypass. For instance, if you had a water pump and you wanted to keep the water cool and moving through that stuffing box, and you didn't want the water to be stagnant around the seal. In other words, it gets in there around the seal in the stuffing box and it doesn't move through, and it holds it there, and the faces generate heat. Well, heat is your enemy. So we want to keep it cool and keep it clean. So what we'll do is we'll go to the discharge of the pump, and we'll use we'll tie it to the discharge of the pump and run the fluid off the discharge back through the seal, and to keep that fluid circulating through that stuffing box to help keep that cool. And you'll see things like on condensate services, hot water. You'll run coolers. You'll come off the discharge and you run the water through coolers and cool it down and inject that water back into that stuffing box at a cooler temperature than what the pump is pumping at. And that keeps that face cool to keep you from having issues pumping hot water. Then also you can have a suction bypass. For instance, if you had an application where you've got higher stuffing box pressures than you would like, you can actually reduce that stuffing box pressure by tying a line back from the seal back to the suction of the pump, and you'll lower the stuffing box pressure closer to the suction pressure. This eliminates and helps take care of situations where you have elevated stuffing box pressures. Now let's talk a little bit about double seals. We talked about single seals. Let's talk about double seals a minute. Double seals are nothing more than two mechanical seals ran back to back. So you got two sets of faces instead of one, is illustrated in this drawing. So in most cases, double seals are ran in a double arrangement. So what you're doing is you still have a port that you flush through, and you're sealing the fluid internally in that seal cavity from the stuffing box. And you see where it's illustrated here in the blue, the fluid doesn't go into the stuffing box, it's just inside the seal itself. So what you're doing is you're actually, say for instance, you had latex or a glue that you knew that you could not seal with a single seal because it'll tear the faces up. You could run a fluid through these two seals at a higher pressure than what the stuffing box pressure is. Now, people are going to say, well, what's the stuffing box pressure? And how do you know this? The best way to determine what a stuffing box pressure is in the pump is put a gauge on it. Also be aware that in some processes they steam, which causes a problem. If you run 150-pound steam in there, obviously your barrier fluid pressure when you're running in a double mode will not overcome 150 pounds of steam pressure. So they can steam pumps and clean pumps, they just can't run them when they're doing it. It won't hurt the seal to steam it, but you can't run the seal while you're steaming it, okay? But what you're doing with this again is you're running that fluid in between those two seals that are set up back to back, like in this illustration. at 15 to 25 psi above what your stuffing box pressure is. That allows that seal to run in double mode. And what you're doing now that that pressure is higher in that cavity internally in the seal than what the stuffing box pressure is, you're running that cool, cleaner fluid across that internal seal face and keeping that seal face lubricated by what you're injecting in the seal, not by the process fluid trying to overcome that and going into the seal across the seal faces from the other side. And that's the proper way to get reliable service out of a double seal in a double arrangement. Some mechanical seals that are double seals, they run them in a tandem arrangement. A tandem arrangement means that your pressure in your stuffing box is greater than the pressure that you're running through the seal as a barrier fluid. And you use this to control toxic emissions, uh, materials that you can't allow to escape the atmosphere. You're basically running the outside set of seal faces as a backup to the internal set of seal faces in the stuffing box. But you never use this with slurries. Slurries will run across the inboard seal face and destroy the inboard seal face, and you won't get proper seal life out of it, because if you have a slurry, most of these arrangements you see like this are in very clean products, that are in clean chemical products that will not damage seal faces. A typical barrier fluid arrangement, this kind of illustrates how this works. You run a fluid from a supply source into the seal, out the top of the seal with a pressure gauge and a valve to actually pressurize the space internally in the seal, the internal spaces within the seal, but between the two seal faces, two sets of seal faces. And you need to run a pressure gauge on that stuffing box to keep up with and find out what that stuffing box pressure is, and set that pressure gauge on the outflow at 15 to 20 psi above that stuffing box pressure. It's always best to gauge that stuffing box pressure. People have all sorts of calculations they use to determine that, but the most reliable way is to gauge it. And if you suspect that the customer may run that seal, may do something to that process that may see an elevated pressure in that stuffing box, they make gauges that have a little indicator on the gauge that if over time the pressure gauge moves above a certain point, it leaves that little indicator needle in place, so you can find out truly what that box pressure is based on system upsets. They may run the pump against throttled head, or may do some cleaning process you don't know about and cause you seal issues. But that little I call them little tattletale gauges, will tell you exactly what conditions that seal sees that they don't even, in a lot of cases, the customers don't even know that seal is seeing those situations. So this is the other thing you can do with seals. If you don't want to use water as a barrier fluid in double seals, you can put in closed loop systems similar to what you see here. And those closed loop systems use a tank that you can put an oil in, synthetic oil. And what happens is a lot of seals have pumping rings in them to pump that fluid through, and double seal lubrication. These are all for double seal lubrication. And what happens is the fluid, as it's heated in the seal faces, in that cavity in the double seal, is heated, and the fluid rises and flows back into this tank and circulated out of this tank. As it cools, it falls to the bottom of the tank, and the fluid flows back into the seal from the bottom of the tank. Now, it's critical when you set these up that you know exactly where you place the tank and the elevation you can place the tank. Don't buy these things and put them in and not have a good understanding of the lengths of the piping and all of that, those issues that go with these tanks, because they won't convect correctly if you don't have them set up correctly. So the manufacturer that you're dealing with can tell you the height off the center line of the pump to mount the tank, and the lengths of the piping, and whether to use fin tubing or not use fin tubing on the returns, and all those things, and those all need to be addressed by the tank manufacturer and the seal manufacturer, and they'll help you out with all that stuff. Typical face combinations. This covers about 80% of what most people are going to use. The standard today for most single seals and outboards on double seals is carbon silicon carbide. All of those seals are sealing, clean fluids. The outboard seals on double seals are sealing a clean barrier fluid. You don't see very much carbon to ceramic used anymore, because silicon carbide is so much better, and it's really just a more cost-effective solution. Tungsten carbide and silicon carbide is a common one that you'll see on the inboards of double seals, and on single seals it may see some abrasion where they can't use flush water and they want to run single seals. You'll see some people run tungsten carbide to silicon carbide. You'll see a lot of tungsten to tungsten faces. They're two dissimilar tungstens. So you have a harder tungsten against a softer tungsten for abrasive situations. And silicon carbide in some acids and places where you can't, where the acids will attack carbon, and you can't use nickel bound metals like tungsten for face combinations. So, but these are the most common face combinations you'll see. Elastomer materials, if you're unsure, you can look at any O-ring manufacturer's compatibility chart and double check your elastomer combinations. But we used to use a lot of Viton and EPR, and most seals came with Viton EPR O-rings. Now we use as a standard Affilas. Affilas has a good universal compatibility, and we use a lot of CalRes and ChemRes O-rings in places where you have where Affilas won't cover those applications. So this is a basic smorgasbord of the standard O-rings that you're going to see. Common end suction pump. This is a common end suction centrifugal pump. For those of you who don't know what a pump, where the seals actually go on the pump, the seals actually go in the place of the mechanical, the braided packing in the stuffing box. We remove the packing glands, and the seals are all pretty much cartridge mounted today, and they just bolt up where your standard packing gland goes. And of course, you have pieces of equipment that have multiple stuffing boxes. This is a typical end suction, double suction, end suction centrifugal pump. Some of these pumps you got to be a little bit careful with. Multiple spring seals. Multiple spring seals only take 3 to 5 thousandths thrust. A lot of these pumps find their center when they start, and so you have to be careful with multiple springs. A lot of times they'll move more actually in thrust than what a standard multiple spring seal will take. We actually build cartridge seals for these type of situations and build seals that will take axial movement like that of these pumps that's inherent in these type pumps. But just be aware that these pumps sometimes can cause some problems if you have multiple spring seals. And of course, vertical turbine pumps, you got some of the same situation with the shaft lifting when the pump starts. But all these pumps have just a standard type stuffing box, standard bolting, standard depths, and there's no problem in retrofitting any of these pumps to mechanical seals from packing. Let's talk about things we address when we decide whether a seal can fit. In most cases, all manufacturers, standard ANSI mechanical seals with slotted glands have pretty much a universal fit. But all the manufacturers have charts with their products that tell you whether the seal that you're recommending will fit that application and fit that piece of equipment. And things, all mechanical seals, of course, are bought by shaft size. If you want a 1 3/8 inch single seal, you buy style XYZ with this face combination, this O-rings. Pretty much that's the way you do it. First thing you got to know, of course, you got to know the shaft OD. You got to make sure the stuffing box bore is adequate for the seal, that it doesn't rub the stuffing box bore when you put the seal in, to make sure you got a proper fit. In most stuffing boxes that have at least a 3/8 inch cross section, that won't be an issue. The other thing you got to be aware of when you look at the stuffing box bore is the pump. You got a big bore box. Those take different glands, so you need to know. And a lot of Goulds and Durco and a lot of those people have what they call big bore taper board boxes. So you got to make sure you pick the right gland to go with that. Of course, the stuffing box depth, on how much space we have in the stuffing box. By the nature of cartridge seals, we need to know the distance to the first obstruction. That tells you how much space you got outside the stuffing box to fit the seal, but be aware, it's not all the way back. Your distance is not all the way back to the bearing frame. It's all the way to the end of the sleeve that you're operating on, that you're trying to mount to. So you got to make sure that you got the length of the sleeve and not all the way back to the bearing housing. And of course, the number of studs and the stud size and the bolt circles, all of that's relevant to make sure that everything fits correctly. But like I said, if it's a standard ANSI pump or a standard pump, and if you call your manufacturer and say, I've got pump model number so and so, and it's a standard bore stuffing box, they'll look up the charts for you and help you with the fitment, and that they can tell you whether the product you're ordering will actually fit properly. So one of the big questions is, anytime you have a seal program, is that ugly question about what is your average seal life. Seals, managing seal programs is the key to being successful and having a reliable program. It helps you, locate those bad actors to figure out where most of your seals are consumed. And unfortunately, a lot of people just change seals. But with a seal change, usually comes a rotating assembly change. Nobody changes a seal unless they change a pump. Very rarely do they just change a seal. So, but seal programs that aren't managed well become very, very costly to your company. And evaluating of that is really important. And so you got to really determine what your average seal life is. You need to find that out. It's not real difficult to figure out what your average seal life is. One of the things you got to know how many seals you're running from a particular manufacturer in the plant to manage it. Once you know how many mechanical seals you have in service, all this becomes pretty elementary to evaluate your program. And one of the questions you may want to ask your current supplier is, how many mechanical seals are operating that you have in service in this plant? How many do you have? A real good supplier that's managing your program for you and helping you should know how many seals, pretty close to how many seals you have running in the plant. And that's something that everybody should know, because they've done surveys and they can look it up and they know. And then the other thing you need to know to find out your average seal life is what your average unit usage is. We don't care about the dollars. The dollars will take care of themselves. It's the number of units that you're actually using. And then it becomes real simple math. I mean, you can go to the storeroom, call purchasing, say, well, tell me how many units did we buy from vendor XYZ this year? and then just kind of do the math and do the calculations for yourself to figure out whether you're getting what you want out of a seal program. You know, the target for your supplier should be having a 4 to 5 year seal life. That's a good targeted number to see whether you're getting what you need to be getting out of the investment you're making. A lot of cases, that average seal life is only going to be 2 to 2.5 years, which is it's pretty common, a lot more common than you think. And then it's when it becomes a very costly issue. So once you know what your average seal life is, and once you know what the total take the total population divided by your annual usage, and that gives you your average life. And that's how many years we're getting out of it. So let's take, for instance, if you've got a plant and you have 300 mechanical seals in service and your annual usage is 150 units that you're buying from your current supplier, just do the math. You take your total population divided by your annual usage, and that gives you that 150 units consumption gives you an average of 2 years life. Well, the real target for a plant that's got 300 units should only be about 60 units per year. You know, through attrition, that's giving you an average 5-year seal life. So what does that cost? Okay. What does an extra 90 mechanical seal replacements cost you? I mean, it's a real simple item. It has to be managed right, spec right. But what does it really cost? I've seen studies where that cost, one of the big pump companies did a cost on what that seal replacement cost on just a standard small ANSI pump. This is not a large pump. Based on downtime, loss of use of that piece of equipment, replacement cost, all the things related to replacing that rotating assembly and rebuilding that pump. And it's about $25,000, believe it or not. That's what that pump actually costs you. So the question is, based on that extra 90 units in this hypothetical situation at $25,000, that's $2.25 million of your maintenance budget that could be spent doing other things. And it affects your overall operating expenses, $2.25 million. And I don't know many plants out there that wouldn't be, and many plant managers that wouldn't be tickled to death to have another $2.25 million profit put on their books every year. So this is just kind of a way for you to look at what you're doing, evaluate what you're doing, and to see if this actually you're getting the value for your investment. Because that's what it's all about. It's all about reliability, understanding the face combinations, understanding the simplicity of this item, and solving these reliability issues you have and how that asset affects your mechanical seal life. The mechanical seal is kind of like the canary in the mine. It's going to give you a signal of other pending mechanical issues you have with your equipment before you can tell, because the seal is the most fragile part of that whole pump system, and it will show you issues before you realize you have issues. And the goal is to find what's costing you this $2.25 million is what the goal is. And it's not a real scary subject. It's not real difficult to find. And it's just work with your local vendor and your local supplier and your local manufacturers and identify those problems, and you too can have your successful seal program. So in closing, does anybody have any questions? Laura, is anybody?
We have a couple questions, but please send your questions in. We've got about 15 minutes to answer questions. If we finish early, we'll finish early, but let me get started with the first question. So how frequently do people move from packing in a pump to mechanical seals? Is that something that's rare, or what have you seen?
Well, in the industry where I've spent a lot of my time, it's been pretty common for people based on the reliability issues that's created by not running equipment properly. That's one of the things that kills mechanical seals, is not running equipment as it's designed, because it increases vibration and pressures and all sorts of different things that cause mechanical seals problems. In some cases, when you look at those applications that you cannot solve, you're just taking and throwing money at something you cannot fix. Uh, a, a lot of cases, they go back to packing from mechanical seals, and they find after they do the studies that some of the dilution rate issues and some of the process upsets that they thought they had with a mechanical seal really aren't there. And our job in our industry is to give the customer the most reliable solution in a cost-effective manner. And that's the way you build value with your customers, to make sure that you're doing what's best for them. And you explain the options, and if you can't do A, B, C, and if you can't correct these issues, you can either continue to do what you're doing and throw money at a problem that you can't fix, or we need to find another solution that's more cost effective for you. And it's it's great to sell a seal, but it's also better to solve somebody's problem.
So we've had two more questions come in. The first is, the slide deck will be emailed to everyone with this recording either Wednesday or Thursday. So the slides will be sent to you and the recorded webinar will be sent to you. So that's the answer to one question. The other question is an air seal a mechanical seal?
Technically, yes, because what you're doing is you're sealing with an air pad along a shaft, and you're actually using an air is a gas is a barrier to impede the flow of a processed material to the atmosphere. So technically, yes, it is a mechanical seal.
But it definitely doesn't have seal faces that rotate together. It's all air sealed.
It's all on a pad and a microfilm of air. It's a non-contacting item, where a mechanical seal is a contacting face, instead of packing is a contacting surface. And an air seal, the seal is actually floating on a gas. And that gas could be air, it could be nitrogen, it could be lots of different things, depending on the application. But it's more of in the gas seal family, I would say, but it is a mechanical seal.
Okay. And another question is, you covered it a little bit in the presentation, but what are some steps people can take to decide if they need to change to a mechanical seal?
Basically, do a calculation and decide it, and get a proper return on investment. Look at the app, sit down with the user needs to sit down, or you sit down with the user and help him make the decision based on that criteria, whether it's a process fluid of value, is there a secondary process dilution cost that we have to take water out of a process. There's all sorts of different things that have to happen to that fluid that you're pumping, that you affect at that pump with what you do with packing or mechanical seals. So the best thing to do is just sit down with the user and just go through all of these operational characteristics and all these process issues with them, and look at the cost of all those items, and then decide what the payback period is for that investment.
And that's an interesting segue into next month's webinar, where we will talk about all the process info you might need to spec equipment or come up with an ROI. So that's a perfect segue. I haven't seen any more questions come in. You've got one more opportunity to throw questions at us before we close out for the morning. But again, recorded webinar will be sent with the slides via an email. We appreciate you all joining us today. Chuck, thank you so much for a great presentation as always. Appreciate you taking the time to do this with us.
Thanks for the opportunity.
All right,
I
thanks
hope it helps.
everybody. I'm sorry, go ahead, say what
I
you just
hope it
said.
helps everybody out. I hope the information helps.
Can't imagine that it didn't help people. Thanks again for joining us, guys. We'll get this out to you as soon as possible, and we hope you have a great rest of your day and a beautiful fall, and we'll talk to you again in December. Take care.
Bye-bye.